This is Unit 2, Section 5. Example 1, determining validity without a truth table. Determine whether the following argument is valid or invalid. If Fall River is in Massachusetts, then Boston is in New York. Fall River is in Massachusetts, therefore Boston is in New York. So this type of argument is a symbolic argument which consists of a set of premises and a conclusion. The premises are here above the line, and this is the conclusion. So we might call this P1 and P2 and our conclusion. When we want to do it without a truth table, what we want to do is compare this argument to one of the standard arguments and see if it holds. Before example 1, we learned the argument if P implies Q and P therefore Q. This argument is called the Law of Detachment. Whenever you see an argument that we can write symbolically this way, we can use the Law of Detachment to say that the argument's valid. So let's see if our premises and our conclusion match this Law of Detachment. So if we let P be Fall River is in Massachusetts, and we let Q be Boston is in New York, then we have for premise 1, if P, then Q. For premise 2, we have P, and then for a conclusion, therefore, with this symbol that looks like a triangle but with dots, therefore Q. This matches the Law of Detachment. So it is valid. We proved that the Law of Detachment was valid using a truth table in the notes. Example 2 asks us to determine the validity of the argument. If you visit Fall River, you go to Battleship Cove. Second premise, you do not go to Battleship Cove. Conclusion, therefore, you did not go to Fall River. So we haven't learned any other arguments at this point in the section, so we're going to have to use a truth table to prove it. Let's see what we have here. We have P for our first statement, you visit Fall River. And Q, you go to Battleship Cove. Then our argument here is if P, then Q. Our second is you do not go to Battleship Cove, so not Q. And our conclusion, therefore, you did not go to Fall River, so not P. So the question is that a valid argument? So what we want to know is if we have P implies Q and we have not Q, does that altogether imply not P? So this is going to be where we use our truth table. So we're going to start with P and Q, and then we're going to check out this argument to see if we have a valid argument. So let's put in our true, 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 false, false, true, false, false. Let's go through each of these. I'm going to jump right to P implies Q because it's very easy to see it here. And we're going to remember, I'll put notes up here, P implies Q is only false when true implies false. So we're going to have true, and we're going to have false, and true, and true. Now negation Q will be the opposite of Q, so we'll have false, true, true. And negation P, the opposite of P, so false, false, true, true. So that leaves us with two operations, the and the if then. But we're going to start with the and because it's inside these brackets. And we remember and is only true when both are true. So we're going to have true and false is false. False and true is false. True and false is false. True and true is true. And then we have our if-then statement using the and with the not P. So let's go ahead and do our if-then. Again, remembering it's only false when we have true implies false. Here we have false implies false, so it's true. False implies false is true. False implies true is true. And true implies true is true. So our final answer column is all trues. When you have all trues in your final answer column, then you have a valid argument. And this is our second standard argument, which we call the law of contraposition, sometimes called the law of the contrapositive. So P implies Q, not Q, therefore not P, is the law of contraposition, which we have just shown is a law because it's valid.